Hey, Advanced Geometry, this is Mr. Donaldson, and we're going to do 1.1b notes today. And this is a continuation of section 1.1, the building blocks of geometry, so still working on the fundamentals. And today's focus is on intersections and then parts of lines. So let's start by talking about intersections. All right, now when I say that word, I imagine that most of you think about the intersection of two roads. All right, talk about an intersection of two roads. You'll notice that this is a road, and it intersects this road maybe. Well, their intersection is this little square right here in the middle. All the points where both those roads have in common will be their intersection. And you're all pretty familiar with that, I would imagine. So, intersection of two geometric figures is exactly the same. It's just a set of all points they have in common. So we're going to run through different types of intersections and what those intersections would be or look like, and we'll go from there. So first is the intersection of two lines. So if you have two lines just floating around in space, there are three possibilities. One possibility is that those lines could intersect one another. And over in my diagram, line LH intersects line HK, and their intersection is only points they have in common, and those two lines, the only point they have in common is H. So they intersect at a point. So anytime two lines intersect, the intersection must be a point. Next possibility is that the lines don't intersect, and that's true for both of these. And you can see I've already typed in, to kind of save you my bad handwriting, some explanations of this. So lines are parallel, and there's a little symbol for parallel. It looks like a kind of a slanted 11. All right, it means parallel lines. If lines are parallel if they're coplanar, so they're on the same plane, but they never intersect one another. Like if you put a sheet of paper down on your desk and you look at both those kind of vertical edges of the sheet of paper, well, your desk is a plane, and those sides of the sheet of paper will never cross one another. Now, we use this symbol, looks like a little arrow, and you see there's one little arrow here and one little arrow here. In geometry, that means that those lines are parallel. We'll talk more about that a little bit later. You can't just look at a diagram and assume that lines are parallel. You'd have to be given those markings. So I know in this diagram that line EG is parallel to line LH, which means they would never intersect. So parallel lines will never intersect. Then there's skew lines. Skew lines are kind of, the same idea as parallel regarding the fact that they're never going to intersect one another, but the difference is skew lines are non-coplanar. So if you look, this is a three-dimensional drawing. You look at this edge of the box here, EG, if it extended forever, and this edge of the box, if it extended forever, they would never intersect one another. I know it looks like those lines would meet on this plane, but you have to visualize this as a three-dimensional drawing. And if it is, then EG and HK are skew, which means they're non-coplanar, and therefore they could never possibly intersect. So they would never intersect. Next, what about a line and a plane? So the first, imagine taking that sheet of paper that you're writing on and taking your pencil and stabbing it right through the middle of the sheet of paper. Kind of like line M is doing to plane P. All right, and this little dotted line means that's part of the line you wouldn't be able to see if the plane, was shaded in or something. You couldn't see through the plane. And that's to indicate that it's a three-dimensional drawing. All right? So if a line and a plane intersect one another, their intersection could be a point. And that's exactly what's happening here. Line M intersects plane P at point F. So the intersection could be a point. There's another example, though. What about, where does line IF intersect plane P? Now remember, intersection is all the points that the two figures have in common. Well, if this line is on this plane, it's contained in the plane, then all the points on line IF that are also on plane P will be every single point. So it's possible for a line and a plane to intersect in a line. And then the last example is that the line and the plane are parallel to one another. And I didn't draw one on here, I should have, but imagine like a little horizontal line just kind of floating up here above this plane. Kind of like if you drew a line, you took a ruler and drew a line on your ceiling, that line that you drew on your ceiling would never intersect the floor. So this line won't intersect this plane, which means they're parallel, so it means there's no intersection. That's what parallel means for a line and a plane that will never intersect. And the last example here is two planes. So I have two planes, and these two planes, plane TUO, is intersecting plane YZ. I believe that's maybe an N. It's kind of blurry to me. Maybe an H. We'll call it N. Okay, this guy right here. So those two planes, TYO and YZH, this vertical plane, this horizontal plane, they intersect right here. And remember, planes go on forever, then so do their intersections. Which means that if planes intersect, they always intersect to form a line. Okay, planes intersect, they always intersect to form a line. Even though this drawing looks like it's a line segment, you must have that conceptual understanding that planes continue forever, and so therefore do their intersections. And the last example is if you have parallel planes. I don't have one drawn here, but you guys, that's pretty easy for you to imagine if you're sitting inside. The floor and the ceiling in the room you're in are parallel. Unless your house was poorly constructed, if you extended your floor and ceiling, they should never intersect. So no intersection here with parallel planes either. Alright, so that is all the different possibilities of intersections with lines and planes. Let's do a couple examples. Alright, so first, let's name three collinear points. I mean, we did this the other day. It's just a review. Remember, when you're naming points, you got to list them with commas, or else I think you're talking about a plane. So I just want 3 points that are on the same line. There's a couple answers here. I'm going to go with B, C, and H. So I'd say B, C, and H. Next, name 3 non-collinear points. This time I want 3 points that are not all on the same line. And the easiest way to go about doing this is just pick 3 points that are, or excuse me, pick 2 points that are on the same line. How about like B and H? And then just pick one more point that's not on that line. So if I pick B and H, I want to pick a point that's not also on this line. So how about F? Those 3 points, B, H, and F, are not all on the same line. They're non-collinear. The intersection of plane A, here's plane A, the yellow plane, and line KF. KF is this line that's vertically going through the plane right at point C. So just point C. The intersection of line BH, here's line BH, and line KF. And the only place that those two lines touch each other or have in common is, again, point C. Next, naming 4 coplanar points. You guys, I just want 4 points that are all on the same plane. Alright? And I'm going to kind of throw you guys a curveball here. Now, one obvious answer would be B, C, H, and E. B, C, H, and E are all on this yellow plane. But check this out. What about B, C, H, and K? Those are also coplanar. Now, I know the plane is not drawn, but most certainly there exists, I'm going to try my best to draw it, a plane. Oh, man, that's bad. That's really bad. Oh, man. Let's try that again. There's a plane, vertical plane, that exists there. All right? So B, C, H, and K could also be labeled as coplanar. Even though the plane's not drawn, it still exists. And for non-coplanar points, non-coplanar means they're not all on the same plane. So I want to pick 3 points that truly identify a unique plane, maybe B, E, H. Notice B, E, and H identifying this plane A. And then I'm just going to pick any point that's not on that plane that I've just identified. So B, E, and H, and then how about point K for non-coplanar points. All right, next, parts of a line. Now I went ahead and typed this in before I started filming, or recording rather, because my handwriting's so terrible on this tablet. So here we go. A line segment is part of a line bound by 2 endpoints. Here's my line segment. Notice the line is not extended with arrows. All right. If you want to name a line segment, it's just like naming a line, except for instead of putting a line with arrows on top, you just put a segment. There you go. So I can name this segment KJ or JK. It doesn't matter which order. It just has the endpoints at the end. And unlike a line that extends infinitely, a line segment has a finite length that you can measure. So this, suppose I took my ruler out and I'm like, oh, that's 8 inches long, which obviously it's significantly less than that, but let's just pretend it is. Then I would say, hey, that segment has a length of 8 inches, and there's a notation for that, and that is just like this. If I just wrote KJ and I have no notation, no line, no segment, nothing on top of it, This implies distance. All right, so no notation when you're dealing with 2 points implies distance or length, because you know both are the same thing. So this reads, the distance from K to J equals 8, or the length of segment KJ is 8 inches. I'm going to use a little inch mark for that. All right, next, congruent segments. This symbol means congruent. It's just an equal sign with a little tilde on top. And congruent segments are segments that have equal lengths. And sometimes in a diagram, it's really helpful if you could see which segments are congruent so that you could start come up with ideas about what's going on. So what we'll do is we'll use what are called congruency marks. And they're just little tick marks. So if I know that DG is congruent to EF, I can mark they're congruent. If I know that DE is congruent to GF, I can mark they're congruent. But there's a problem right now. I have one tick mark on every segment, but not all segments are necessarily congruent. So if you wanted to have a different set of congruent segments, you could use 2 tick marks, or 3 tick marks, or 4 tick marks. So by looking at this picture, I know DG is congruent to EF, and DE is congruent to GF. Next, array. Array is part of a line that's bound by one endpoint and continues indefinitely in one direction. And when you're naming array, really important, you always name the endpoint first. So this is ray AB. Put a little ray on top, like it says here. And this would be ray CD. And you just put a little ray on top. Now I know that the ray is pointing this way in the diagram, but when I name it, you always point that arrow to the right. All right, a couple examples real quick. All right, name the intersection of plane GFE. GFE is the top of the box, GFE, and EFL. EFL is the right side of this box. Well, they intersect right here. Now remember, planes go on forever, so do their intersections. So they intersect at line EF. If I ever ask you where planes intersect, and they intersect each other, it's always a line. Name the intersection of planes IHK. So here's IHG. IHG is the left side of the box, and HGK. Now this is kind of tricky. You might look and say, hey, HGK is not a plane. But remember, any 3 points defines a plane. There's a plane that exists here. It's a little diagonal plane. You just can't see it. It's not drawn. But where that diagonal plane intersects the left side of this box is at line HG. Name the plane that represents the bottom of the box. Well, to name a plane, I need 3 non-collinear points. So how about JIM? Let's call this plane Jim. Name 2 congruent segments. Well, I'm going to name my segments are congruent only if they have congruency marks, and I see that GH is congruent to EF. Name a ray with endpoint M. I'm just going to name any ray I want that starts at M. So remember, planes go on forever. So that means this ray, MK, goes on forever. Or this ray, MI, goes on forever. And just because things aren't drawn doesn't mean they don't exist. Even ray ME would work. Really, you're just going to start with M and just pick any other point in the diagram, and there's a ray that starts at M and goes through that other point. So I name it ray MI in this example. This says KL is equal to. Now remember, there's no segment on top, so it's not congruency. There's no line. This means the length of KL is equal to. Well, what is the length of KL? Over my diagram, I see it's 15 centimeters. Name 2 parallel lines. So this time I'm looking for parallel marks. And I go to my diagram and look, HE is parallel to GF. And the way you write that is just like this. Say, all right, HE with a line on top, because I want parallel lines. Planes go on forever, so go to those lines. And that's parallel to GF. Oops. All right. Next, any 3 points in space are always coplanar. We talked about this last week. That's a gimme. If I ever ask you about 3 points, no matter a picture or not, you always know they're coplanar because any 3 points can always define a single plane. Given a line that intersects a plane, the intersection is blank a line. This is sometimes. Remember, there's 2 choices. There's the line contained in the plane, or there's a line poking through the plane. Sometimes the intersection is a line. And last but not least, given 2 planes that intersect, their intersection is blank a line segment. That is never, because I told you guys, if 2 planes intersect, they always intersect to form a line. All right, you guys, thanks for watching. Hopefully that made sense. Let me know if you have any questions. Have a great day.